Hi, my name is Nishil, and in this video, I'm going to talk about our paper called Prodigy that addresses the memory latency problem in irregular workloads. This is a collaborative work with my colleagues at the University of Michigan, University of Wisconsin-Madison, and the University of Edinburgh. Huge amounts of data are being generated by digital services that we use every day. This is even more significant during the COVID-19 pandemic when most of our daily activities have moved online. To provide useful and efficient experience, these services must analyze the information that we generate every day. For example, food delivery services optimize their inventory and delivery routes to fulfill our orders quickly and cheaply. Streaming platforms like Netflix employ powerful recommendation systems to keep us engaged. Social media websites help us expand our personal and professional networks. And finally, credit card companies keep our finances secure online. Studying, analyzing, and deriving useful insights from all of this information is known as big data analytics, and it is only growing in its popularity. While using all of these wonderful technologies, we are generating more and more data every year. On the other hand, the latency of memory units used to store this data is almost stagnant. Hence, intuitively, memory systems can become a major bottleneck in these tasks. To test this hypothesis, we analyzed a wide range of applications from graph analytics, linear algebra, and scientific computing domains, only to find out that these applications spend about three-fourths of their execution time just waiting to receive data from the memory system or the DRAM. So yes, the intuition is correct indeed, and the memory system is a real bottleneck in these workloads. Let's understand this further. In addition to using large amounts of data, these applications also make use of sparse data structures, for example, compressed sparse row or CSR, to conserve space by storing only non-zero values. This comes at a cost of more complicated algorithms that use data-indirect memory access patterns, for example, A of B of I, that exhibit low locality. This work proposes Prodigy, a hardware-software co-design solution in order to alleviate the memory latency bottleneck in these irregular workloads. Specifically, we use the best of both worlds approach by employing both hardware and software to do what they're best at. The heart of our proposal is the data indirection graph, or a DIG information that communicates key workload characteristics from software to hardware. Specifically, it is a weighted graph that abstracts the notion of program semantics of a given workload. As software has the static view of program instructions, we assign software to find the existence of irregular memory accesses in a workload. Compiler analysis is used to capture these program semantics that include layout and memory access patterns of key data structures. They are then bundled in the form of data indirection graph, which is used to make a hardware prefetcher cognizant of an irregular algorithm's behavior and prefetch accordingly. The main motivation for employing hardware prefetching over its software counterpart is to exploit runtime information available to hardware in order to maintain prefetch timeliness by dynamically adapting to an application's execution pace. This gives rise to our system that we call as Prodigy, as it employs software analysis coupled with hardware prefetching using a program's DIG information. We show that Prodigy enjoys significant performance and energy benefits at a negligible hardware cost. For example, Prodigy improves the performance and energy consumption of a non-prefetching baseline by 2.6 and 1.6 times on average, respectively, by merely using zero point 0.8 kilobytes worth of storage space. Furthermore, we also show that Prodigy outperforms the state of the art prefetching approaches as well. With that, thank you for watching and please check out our paper for more details. Now I'm happy to take any questions.